Hello everyone. Today let us discuss about equipotential line of constant stream function, flownet, relationship between stream function and velocity potential function, types of motion that includes linear translation or pure translation, linear deformation, angular deformation, rotation and its related problems. Now let us first discuss about equipotential line. So what is equipotential line? Let us just define equipotential line as this. A line along which the velocity potential that is represented by phi is constant is called equipotential line. So value of velocity potential function that is phi remains same along the line. So that is called as equipotential line. For equipotential line, phi equal to constant. So differentiate above expression phi equal to constant. So upon differentiating we get d phi equal to differentiation of constant that is equal to 0. Therefore d phi equal to 0. But for two-dimensional case, phi is a function of x and y. So for steady flow state, we can write expression as d phi equal to dou phi by dou x into dx plus dou phi by dou y into dy. But from velocity potential definition, we have values for u and v as u equal to minus dou phi by dou x, v equal to minus dou phi by dou y. So just substitute in that above expression in d phi. So d phi equal to dou phi by dou x dx plus dou phi by dou y into dy, that becomes minus u dx minus v dy. So taking minus outside, that is equal to minus into u dx plus v dy. So for equipotential line from above expression we have d phi equal to 0. So equating above expression to 0. So we get minus into u dx plus v dy equal to 0 or u dx plus v dy equal to 0. Just simplify the above expression in order to get dy by dx, that is actually a slope of equipotential line. Therefore dy by dx equal to minus u by v. Take it as equation 1. Now let us go for line of constant stream function. So it is again similar to velocity potential function. Instead of velocity potential function, along the line value of stream function that is represented by xi is constant. So xi equal to constant, differentiating again, d xi equal to differentiation of constant that is again equal to 0. Therefore d xi equal to 0. For two-dimensional steady flow case, we can write expression as d xi equal to dou xi divided by dou x into dx plus dou xi divided by dou y into dy, that is equal to v dx minus u dy. That is because from definition of stream function we have dou xi by dou x equal to v, dou xi by dou y equal to minus u. So for a line of constant stream function d xi equal to 0 from above expression. So therefore v dx minus u dy equal to 0. Just simplify this expression in order to get dy by dx, that is equal to v by u. But dy by dx equal to slope of streamline. So from equation 1 and 2, it is clear that the product of slope of equipotential line and line of constant stream function is equal to minus 1. Otherwise we can describe the equipotential line are orthogonal to streamlines at all points of intersection. So now let us discuss about flownet. What is flownet? So flownet, a grid obtained by drawing series of equipotential and streamlines is called a flownet. So you have to draw a number of streamlines along with number of velocity potential. Whatever the grid you are going to get from that is called as a flownet. The flownet is a very important tool in analyzing two-dimensional irrotational flow problems. That is, it finds application in solving the problems of irrotational flow. Now let us go for relationship between stream function and velocity potential function. Relationship between stream function and velocity potential function can be obtained as follows. But from definition of velocity potential function, we have u equal to minus dou phi by dou x, v equal to minus dou phi by dou y for two-dimensional case. Again similarly for a stream function, dou xi divided by dou x equal to v, dou xi divided by dou y equal to minus u. Therefore we have u equal to minus dou phi by dou x, that is from velocity potential function, and minus dou xi divided by dou y, that is from stream function. Similarly we can write expression for v as v equal to minus dou phi divided by dou y, that is from velocity potential function, that is equal to dou xi divided by dou x, that is from stream function. So hence we can equate dou xi divided by dou x, that is equal to dou xi divided by dou y, that is equal to u, and again dou phi divided by dou y, that is equal to minus dou xi divided by dou x, that is equal to v. There is a relationship between a stream function and velocity potential function. Now let us go for types of motion. So there are four types of motion. Let me discuss about this thing. A fluid particle while moving may undergo any one or combination of following four types of displacement or types of motion. So let us go one by one. First one is linear translation, otherwise it is called as pure translation. Second one is linear deformation. Third one is angular deformation, and fourth one is rotation. Now let us first go for linear translation. Now what is linear translation? It is defined as movement of fluid element in such a way that it moves bodily from one position to another position, and the two axes AB and CD represented in new positions by A dash B dash and C dash D dash are parallel. So initially the fluid element has axis AB and CD. You can see that is represented in XY plane. Because of the deformation or the motion, it goes to new position, or it moves bodily from one position to older position to new position. In that new position, the axis is represented by C dash D dash and A dash and B dash, and those two are parallel to each other. That is the AB and A dash B dash, that is parallel, and C dash D dash and CD, that is parallel. Now let us go for linear deformation. It is defined as deformation of a fluid element in a linear direction when the element moves. The axes of the element in the deformed position and undeformed position are parallel, but their length changes. It is similar to the motion along a longitudinal direction. You can see there initially the fluid element has axis AB and C dash. Because of the deformation along linear direction, it undergoes it goes to new position. Because of that, A dash B dash and C dash D dash, that is a new axis, but length of A dash B dash compared to AB, that is different, and similarly C dash and C dash D dash and CD. So but they remain parallel to each other in deformed position as well as undeformed position. Undeformed position means there's an original position. Deformed position is final position. Now let us go for angular deformation or shear deformation. There is a third type of motion. So it is defined as every change in the angle contained by two adjacent sides. Let delta T1 and delta T2 is a change in angle between two sides of a fluid element. Then the angular deformation or shear strain rate is given by, that is equal to 1 by 2 into delta T1 plus delta T2. Just remember, delta T1 is the angular change with respect to x-axis, and delta 2 is the angular change with respect to y-axis. So just remember this expression, angular deformation equal to 1 by 2 into delta T1 plus delta T2, or that is called as shear strain rate. This relation is very important for solving the problem. For time's sake, just remember this expression as shear strain rate equal to 1 by 2 into dou v by dou x plus dou u by dou y. Now angular position deformation, that is represented in this diagram. You can just see there delta T1 is the change in angle with respect to x-axis, and delta T2 is the angular change with respect to y-axis. Now let's go for rotation. This is the last type of motion. It is defined as movement of fluid element in such a way that both of its axes, that is horizontal as well as vertical, rotate in same direction. For example, you can see the diagram AB and CD. So AB that rotates in anti-clockwise direction, that goes to A dash B dash. Similarly CD that rotates in anti-clockwise direction and it goes to new position C dash D dash. And now you know the rotational component from previous slide, that is Wz equal to 1 by 2 into dou v by dou x minus dou u by dou y for a two-dimensional element in xy plane. In order to get rotational component in xy plane, that is Wz, you are supposed to write. So the rotational components in other planes, that xy plane, yz plane and zx plane can be obtained as follows. Wz equal to 1 by 2 into dou v by dou x minus dou u by dou y. Wy equal to 1 by 2 into dou u by dou z minus dou w by dou x. Wx equal to 1 by 2 into dou w by dou y minus dou v by dou z. You have to remember these three expressions. That is very important for solving the problem. Now what is it? Last definition in second module. It is defined as the value twice the rotation, that is it is equal to 2 into wx, or that is equal to 2 into wy, or that is equal to 2 into wz, is actually equal to 2 times the rotational component. Now let us go for solving the problem. First problem, velocity potential function phi is given by expression phi equal to minus xy cube divided by 3 minus x square plus x cube y divided by 3 plus y square. Find the velocity components in x and y direction. Show that phi represents a possible case of flow. So let us go for solution. Given, just write down the given expression. That is for velocity potential function phi equal to minus xy cube divided by 3 minus x square plus x cube y divided by 3 plus y square. So just differentiate above expression with respect to x and y. We get dou phi divided by dou x. Differentiating above expression with respect to x, differentiation of minus xy cube divided by 3, that becomes y cube divided by 3 minus differentiation of x square, that is 2x, plus differentiation of x cube y divided by 3, that is differentiation of x cube is 3x square into y divided by 3. Similarly, differentiate above expression with respect to y. Dou phi divided by dou y, that is equal to minus 3xy square divided by 3 plus x cube divided by 3 plus 2y. Take it as expression 2. Now velocity components u and v, that is given by, from definition of velocity potential function, u equal to minus dou phi by dou x and v equal to minus dou phi by dou y. But we have expressions for dou phi by dou x and dou phi by dou y. Just substitute u equal to minus into whatever you have obtained by differentiating with respect to x, minus into minus y cube by 3 minus 2x plus 3x square y divided by 3, multiplying minus side inside, that becomes y cube divided by 3 plus 2x minus x square y. Similarly, v equal to minus dou phi by dou y, that is equal to minus into minus 3x y square divided by 3 plus x cube by 3 plus 2y, multiplying minus side inside, that is equal to 3x y square divided by 3 minus x cube by 3 minus 2y, that is equal to, upon rearrangement, xy square minus x cube by 3 minus 2y. That's the answer for first case. That's the velocity components in x and y direction. Now let us go for calculation of second point, that is the given value of phi will represent a possible case of flow if it satisfies the Laplace equation. So Laplace equation for velocity potential function is given by dou square phi divided by dou x square plus dou square phi divided by dou y square equal to 0. You have to remember this expression, Laplace equation, in order to show whether it satisfies Laplace equation or not. From equations 1 and 2, that is dou phi by dou y and dou phi by dou x, we have dou phi by dou x equal to minus y cube by 3 minus 2x plus x square y. Differentiating above expression with respect to x again, dou square phi divided by dou x square equal to minus 2 plus 2xy, and dou phi by dou y from equation 2 equal to minus xy square plus x cube by 3 plus 2y. Differentiating again with respect to y, dou square phi divided by dou y square, that is equal to minus 2xy plus 2. Therefore, dou square phi divided by dou x square plus dou square phi divided by dou y square, just substitute the values of dou square phi divided by dou x square and dou square phi divided by dou y square, that is equal to minus 2 plus 2xy plus minus 2xy plus 2, that is equal to 0. So it satisfies Laplace equation. Therefore, phi represents a possible case of flow. This is the first problem. Very simple problem. You need to remember expression for u and v from velocity potential function and Laplace equation, and you have to just differentiate and substitute in Laplace equation and just calculate whether it is going to satisfy Laplace equation or not. If it satisfies Laplace equation, then it is a possible case of flow. Otherwise, it is an impossible flow. Now let us go for second problem. The velocity potential function is given by phi equal to phi into x square minus y square. Calculate the velocity component at the point 4, 5. There is one point is given, that is 4, 5. You need to calculate velocity potential value at that point. Now we have to write, what we have to do is just write down the given content, that is given data is phi equal to phi into x square minus y square. Now differentiate phi with respect to x and y. Dou phi by dou y, dou x equal to 10x, dou phi by dou y equal to minus 10y. But from definition of velocity potential function, we have values of u and v. U equal to minus dou phi by dou x, so we get u equal to minus 10x, and v equal to minus dou phi by dou y, that is equal to minus into minus 10y, that is equal to 10y. So velocity components at the point 4 comma 5, that is at x equal to 4, 4 corresponds to x value, 5 corresponds to y value. Just substitute u equal to, we have expression for u equal to minus 10x. In place of x you substitute 4, so minus 10 into 4, that is equal to minus 40 units. V equal to 10 into 5, that is y value, y value is 5, just substitute in place of y as 5, 10 into 5 equal to 50 units. That's the answer. This is the second problem. Now let us go for third problem. Stream function is given by phi equal to xi equal to 5x minus 6y. Calculate the velocity component and also magnitude and direction of resultant velocity at any point. So just write down given of content or data, that is xi equal to 5x minus 6y. So from definition of stream function, we have values of u and v. Let me discuss about that thing later. Now just differentiate xi with respect to x and y. Dou xi divided by dou x, we get phi, and dou xi divided by dou y, that is equal to minus 6. But the velocity components u and v in terms of stream function is given by definition of a stream function as u equal to minus dou xi divided by dou y, and v equal to minus dou xi divided by dou x. So just substitute values of dou xi and dou x, we get u equal to minus dou xi divided by dou y, that is equal to minus into minus 6, that is equal to 6 units per second, because unit of velocity is meter per second, but nowhere unit of velocity is mentioned as meter per second. So just write in place of meter, you just write units per second. Similarly, v equal to dou xi divided by dou x, that is equal to 5 units per second. Resultant velocity, you know, I already calculated this thing in previous local acceleration and convective acceleration. Resultant velocity equal to square root of u square plus v square. Now we have values of u and v, that is equal to square root of 6 square plus 5 square, that is equal to root 61, or that is equal to 7.81 unit per second. Direction is given by, it is just here to remember this expression. Direction is given by tan theta equal to v by u. There is a velocity in y direction divided by velocity in x direction. Velocity in y direction is 5 and velocity component in x direction is 6. So that is equal to 5 by 6, that is equal to 0.8333. So theta equal to tan inverse of 0.8333, that is equal to 39 degree 48 second. You can write 48 second or you can write 39.5 degree, that is also okay. Okay, let us go for a third problem. If for a two-dimensional potential flow, velocity potential is given by phi equal to x into 2y minus 1. Determine the velocity at the point p 4, 5. Determine also value of stream function xi at the point p. So given that phi equal to x into 2y minus 1. So from definition of velocity potential function, we have u equal to minus dou phi by dou x and v equal to minus dou phi by dou y. So differentiate phi with respect to x and y, we get minus dou phi divided by dou x equal to minus into 2y minus 1, that is equal to 1 minus 2y. Similarly, v equal to minus dou phi divided by dou y, differentiate phi with respect to y and multiply by minus into 2x, that is equal to minus 2x. At the point p, some point is given in problem, p at the point p 4, 5, that is x equal to 4 and y equal to 5. Just substitute in place of x as value 4 and y as value 5. So just get value of u equal to, expression for u is 1 minus 2y. In place of y, you substitute value of y as 5. So u equal to 1 minus 2 into 5, that is equal to minus 9 units per second. V equal to minus 2x, so in place of x, substitute x value as 4. So minus 2 into 4, that is equal to minus 8 units per second. So resultant velocity at p, similar to previous problem, that is equal to square root of u square plus v square. So that is equal to square root of 81 plus 64, that is equal to 12.04 units per second. That's the answer for resultant velocity. Next, this one more thing is given in question. Also determine value of stream function xi at the point p. That means from velocity potential function, we are supposed to find value of xi. So that can be calculated as follows. Value of stream function at p. So we know that from definition of stream function, dou xi divided by dou y, that is equal to minus u. But we have value of u as 1 minus 2y, so that is equal to minus 1 into 1 minus 2y, that is equal to 2y minus 1, just multiplying minus side inside. And similarly, we have expression for v, dou xi divided by dou x equal to v, so equal to minus 2x. Now integrate, take dou xi divided by dou y as one equation, dou xi divided by dou x as second equation. So integrating equation 1 with respect to y, because it's a differentiation with respect to y. So just modify the expression as dou xi equal to 2y minus 1 into dou y. So to integrate equation 1 with respect to y, we get integration of d xi, dou xi, that is equal to d xi here, dou xi equal to integration 2y minus 1 into dy, or for integration of d xi is xi, and integration of 2y minus 1, this integration of 2y is 2 into y square by 2, minus integration of 1 is y, plus some constant of integration. Now constant of integration from this expression, as I already explained in convective acceleration, here it is not a function of y, so it is a function, it can be a function of x. So let the value of constant of integration is k, just assume constant of integration as k, then xi equal to y square minus y plus k. Now differentiating equation, above equation with respect to x, we get dou xi divided by dou x, that is equal to, there is no x term here, so integration of y square and differentiation of y square and y, that is equal to 0. So remaining term is k, so dou k divided by dou x, because k is a function of x. But from equation 2, you can see here equation 2 as dou xi divided by dou x equal to minus 2x. You can just equate now dou xi divided by dou x from equation 1 and 3, equation 2. So we get dou xi divided by dou x equal to dou k divided by dou x. So dou xi divided by dou x value is minus 2x from equation 2. So equating the value of dou xi divided by dou x, we get dou k by dou x equal to minus 2x, because dou xi divided by dou x equal to dou k by dou x. So dou k by dou x equal to minus 2x. Now we have to find value of k. How to find? Now there is a differentiation. You have to cancel that differentiation. That can be cancelled by integrating. So dou k equal to minus 2x into dou x. Now integrating above expression, integration of dou k is k, that is equal to integration of minus 2x into dx. So integration of minus 2x with respect to x is minus 2x square by 2, or 2 that is going to cancel, that is equal to minus x square. So you can substitute back this value of k in equation 3, that is xi equal to y square minus y plus k. So value of k is minus x square. So xi equal to y square minus y plus minus x square, that is the value of stream function. Now they told to find value of stream function at the given point, that is p equal to 4 comma 5. So stream function xi value at p 4 comma 5, in place of y you substitute value as 5, and in place of x value as 4. So 5 square minus 5 minus 4 square, that is equal to 25 minus 5 minus 16, that is equal to 4 units. So that is the answer for value of stream function at point p 4 comma 5. Now let us go for next problem. The stream function for a two-dimensional flow is given by xi equal to 2xy. Calculate the velocity at the point p 2 comma 3. Find the velocity potential function phi. This is the reverse case of previous problem. To find here phi instead of xi. Previous problem was potential function was given. From potential function you determine value of stream function. This is exactly reverse. Stream function is given to find value of potential function. So just write down given data xi equal to 2xy. So from definition of stream function we have u equal to minus dou xi divided by dou y, and v equal to dou xi divided by dou x. Just differentiate above expressions, that is xi equal to 2xy with respect to y and x. So u equal to minus dou xi divided by dou y, that is equal to minus 2x. v equal to dou xi divided by dou x, that is equal to 2y. At the point p 2 comma 3 we get u equal to, in place of x you substitute x value as 2, y value as 3. So we get u equal to minus 2 into 2, that is equal to minus 4 units per second. V equal to 2 into 3, that is equal to 16 units per second. Resultant velocity at p, that is 2 comma 3, we get, that is equal to square root of u square plus v square, that is equal to 4 square plus 6 square, square root of 4 square plus 6 square, that is equal to root 52, that is equal to 7.21 units per second. Now the first point that is over, that is the calculate the velocity at the point, that is the resultant velocity at p 2 comma 3, that is over. Now remaining thing is find the velocity potential function phi. So in order to find velocity potential function, first you have to write expression for velocity potential function. So that from the definition of velocity potential function, we have u equal to minus dou phi by dou x, v equal to minus dou phi by dou y, or dou phi by dou x equal to minus u, dou phi by dou y equal to minus v. So we have values of u and v as u equal to minus 2x, v equal to 2y. So just substitute dou phi by dou x equal to minus 2x, minus into minus 2x, that is equal to 2x. Dou phi by dou y, that is equal to minus v, v value is 2y, so it becomes minus 2y. So integrating it is similar to previous problem. First case you can just integrate, or first equation, with respect to x. So just make the rearrangement as follows: dou phi equal to 2x into dou x. So integration of dou phi is phi, that is equal to integration of 2x dx with respect to x, that is 2x square divided by 2 plus c, that is the constant of integration. 2 and 2, that is going to cancel, so that is equal to x square plus c. Take it as expression 3, where c is a constant which is independent of phi, but it can be a function of y, similar to previous problem. Now differentiating equation 3 with respect to y, we get dou phi by dou y, that is equal to integration of differentiation of x square with respect to y is 0, so remaining term is c, that is a function of y, so that is equal to dou c by dou y. Therefore dou phi by dou y equal to dou c by dou y. But from 2 we have dou phi by dou y equal to minus 2y. Now we can equate 2 and 3 equation. 2 and dou phi by dou y equal to dou c by dou y expression. So we get dou phi by dou y equal to dou c by dou y. From that we can get value of dou c by dou y equal to minus 2y. Now integrate in order to get value of c, to integrate in order to cancel differentiation sign. Integrating this equation, we get c equal to integration of minus 2y with respect to y. This is just cross multiplication, that is equal to integration of minus 2y is minus 2y square by 2, that is equal to minus y square. Now we can substitute back value of c in previous equation, that is phi equal to x square minus y square. That is the equation for velocity potential function. Now let us go for next problem. The velocity components in two-dimensional flow field for an incompressible fluid are as follows: u equal to y cube divided by 3 plus 2x minus x square y, and v equal to xy square minus 2y minus x cube by 3. Obtain an expression for stream function phi. Now given content you can just write down: u equal to y cube by 3 plus 2x minus x square y, v equal to xy square minus 2y minus x cube by 3. The velocity components in terms of stream function, that is from definition of stream function, we have dou z divided by dou x equal to v, that is equal to v value is given in problem itself, xy square minus 2y minus x cube by 3. And dou z divided by dou y, that is equal to minus u. U value is given in problem, minus u equal to minus y cube by 3, just multiply in minus side inside, minus 2x plus x square y. Take it as equation 2. Integrating, similar to previous problem, integrating equation 1 with respect to x, we get xi equal to integration of xy square minus 2y minus x cube by 3 with respect to x. So xi equal to x square y square by 2 minus 2xy minus x to the power 4 divided by 4 into 3 plus some concept of integration, that is represented by k. Take it as expression 3. Now expression 3 differentiate with respect to y. So dou z divided by dou y, that is equal to 2x square y divided by y by 2 minus 2x plus dou k by dou y equal to x square y minus 2x plus 2k dou k by dou y, just a simplification. Now from expression 2 and whatever the expression you have obtained now, that is dou z divided by dou y equal to x square y minus 2x plus dou k by dou y, those are equal. So just compare x square y minus 2x plus dou k by dou y, that is equal to minus y cube by 3 minus 2x plus x square y. Remaining terms will cancel. You can write the expression, whatever the remaining term is, dou k by dou y equal to minus y cube by 3. So there is a value of dou k by dou y. Now the problem is not yet complete, so you have to just not yet completed, you have to just get value of k. That can be done by integrating. K equal to integration minus y cube by 3 with respect to y equal to minus y to the power 4 divided by 4 into 3, that is equal to minus y to the power 4 by 12. Substituting this value in equation 3, that is I equal to x square y square by 2 minus 2xy minus x to the power 4 divided by 12 plus k. You can just substitute the value of k as minus y to the power 4 by 12. So xi equal to x square y square by 2 minus 2xy minus x to the power 4 divided by 12 minus y to the power 4 divided by 12. That's the answer for stream function. Okay, let us go for next problem. In a two-dimensional incompressible flow, the fluid velocity component are given by u equal to x minus 4y and v equal to minus y minus 4x. Show that velocity potential exists and determine its form. Find also stream function. So solution, just write down the given contents. U equal to x minus 4y and v equal to minus y minus 4x. Now just differentiate u with respect to x and v with respect to y. Dou u by dou x equal to 1 and dou v by dou y equal to minus 1. You have to show velocity potential function exists. So from continuity equation, dou u by dou x plus dou v by dou y, that is equal to 1 minus 1, that is equal to 0. So hence flow is continuous and velocity potential exists. So there is phi is velocity potential function. Just define phi as velocity potential function. Now let the velocity components in terms of velocity potential function is given by this from definition of velocity potential function, u equal to minus dou phi by dou x and v equal to minus dou phi by dou y. So otherwise dou phi by dou x equal to minus u and dou phi by dou y equal to minus v. So dou phi by dou x equal to minus u, that is equal to minus into x minus 4y, that is given in problem, equal to just multiply minus sign minus x plus 4y. Similarly dou phi divided by dou y, that is equal to minus v. V value is given in problem, just multiply by minus side inside, minus into minus y minus 4x equal to y plus 4x. Take it as an expression to our equation 2. Now integrating, similar to previous problem, integrating equation 1 with respect to x. So phi equal to minus x square by 2 plus 4xy plus c. This is a constant of integration, where c is a constant of integration which is a function of y and not a function of x. So this constant can be c can be a function of y. That's what I told. Differentiating above equation, that is phi equal to minus x square by 2 plus 4xy plus c with respect to y, we get dou phi divided by dou y. Differentiation of minus x square by 2 is 0. So 0 plus 4x plus dou c by dou y. So but from equation 3 we have dou phi by dou y equal to y plus 4x. Y plus 4x. Equating the values of dou phi by dou y, we get 4x plus dou c by dou y, that is equal to y plus 4x, or dou c by dou y equal to y. Integrating above equation with respect to y, we get value of c as c equal to y square by 2 plus c1, where c1 is constant of integration which is independent of y and can be a function of where c is a constant of integration which is a function of x and it is independent of y. Taking that is equal to 0, we get c equal to y square by 2. So substituting the value of c in equation 3, we get phi equal to minus x square by 2 plus 4xy plus y square by 2. There's a value of velocity potential function. That's what it's a very simple problem. If u and v values are given in problem, just differentiate with respect to x and y and get a value of phi in terms of constant of integration. Then just differentiate this whatever the expression that phi, that is a phi value equal to minus x square by 2 plus 4xy plus c with respect to y. So you get value of dou phi by dou y equal to 4x plus dou c by dou y. So from equation 2 we have dou phi divided by dou y equal to y plus 4x, and whatever the expression we have obtained here, that is dou phi by dou y, that is equal to 4x plus dou c by dou y, just compare. So in place of dou c by dou y, we are going to get value of dou c by dou y equal to y. So now once you get dou c by dou y value, you can just integrate with respect to y in order to get value of c equal to y square by 2 plus, or you can just directly neglect this constant c equal to y square by 2. So taking you can substitute value of c equal to y square by 2 in above expression, that is phi equal to minus x square by 2 plus 4xy. So C value is y square by 2. So expression for potential function that becomes phi equal to minus x square by 2 plus 4xy plus y square by 2. That's the answer. Now last problem. The velocity components in a two-dimensional flow are u equal to y cube by 3 plus 2x minus x square y and v equal to xy square minus 2y minus x cube by 3. Show that these components represents a possible case of irrotational flow. So first write down given contents, that is u equal to y cube by 3 plus 2x minus x square y. Differentiate with respect to x, dou u by dou x equal to 2 minus 2xy, dou u by dou y equal to 3y square by 3 minus x square. This is a differentiation with respect to y, that is equal to y square minus x square. Also we have expression for v, that is equal to v equal to xy square minus 2y minus x cube by 3. So again differentiate v with respect to x and y. So dou v by dou y equal to 2xy minus 2, dou v by dou x equal to y square minus 3x square by 3, that is equal to x square y square minus x square. For a two-dimensional flow, continuity equation is given by dou u by dou x plus dou v by dou y equal to 0. So substitute the value of dou u by dou x and dou v by dou y from above expressions. We get dou u by dou x plus dou v by dou y equal to 2 minus 2xy plus 2xy minus 2, that is equal to 0. When it satisfies continuity equation, we can tell is a possible case of fluid flow. Now in order to see whether it is a flow is irrotational, rotational, you should go for rotational components. So rotational component in xy plane, one thing I should ask here, why we have to consider rotational component in xy plane? That is just because here velocity components in x and y direction is given, that is u and v. So I have to go for rotational component in xy plane, that is given by wz. Wz is given by, that is equal to 1 by 2 dou v by dou x minus dou u by dou y, that is equal to substitute the value of dou v by dou x and dou u by dou y in that expression for wz. So that is equal to 1 by 2 into y square minus x square minus y square minus x square. So that is equal to 0. So rotational component in xy plane is 0, which means that is a case of irrotational flow. There's like a fluid element is not going to rotate. It is directly flowing. So these are the problems that is related to second module. Just practice these problems, very easy. You have to just differentiate with respect to x and y, and you have to integrate with respect to x and y and get the value of constant of integration. And you have to in other cases it is like you have to just get the value of u and v. There's a velocity components in x direction and y direction, and find out velocity in x and y direction and find out the resultant velocity, and I have to find out the direction of resultant velocity by tan theta equal to v by u, and resultant velocity equal to square root of u square plus v square. And main thing is you have to remember here velocity components by using velocity potential, that is dou phi by dou x equal to minus u, dou phi by dou y, that is equal to minus v, and from stream function dou xi divided by dou x, that is equal to minus u, and dou xi divided by dou y, that is equal to u. So those are the things you are supposed to remember here. Sorry, dou xi divided by dou x equal to minus u v, and dou xi divided by dou y equal to minus u. This is the expression you are supposed to remember. If you remember those expressions, this problem is nothing. You can directly solve. There is a problem for 10 marks, or you can expect for 12 marks. So thank you.